Hello friends, welcome to this lecture. In this lecture we will continue our study of wave equation, and if you recall in previous lecture we have discussed the one dimension wave equation, and we discussed the D'Alembert solution for one dimension wave equation, and now we continue our study from that onward. So, we have discussed the a string problem of infinite length, and the solution is known as D'Alembert solution. Now, let us move to semi-infinite string. So, it means that now consider the motion of a semi-infinite string. So, here your x is lying between 0 to infinity. So, x is greater than or equal to 0, having one end fixed at the point x equal to 0. So, it is like this, you have this point, and from here it is already fixed. So, at x equal to 0 your string is fixed at point x equal to 0. Now, the condition initial and boundary condition are given like this, that initial shape of is given as u equal to f of x, and initial velocity w by t is given as g of x at x greater than or equal to 0 at t equal to 0. So, initial displacement and initial velocity is given by this, and since one end is fixed at x equal to 0, so here we will introduce boundary condition as well. So, here at x equal to 0 your u is equal to 0 and w by t is also 0. So, at this fixed point your displacement as well as the velocity is 0. So, at t greater than or equal to 0 and x equal to 0. So, here this is fixed. So, your position as well as velocity will remain 0 for all time t greater than or equal to 0. And if you look at here, we cannot apply the D'Alembert solution directly, because if you remember your solution will be what, u x t equal to half of f of x plus c t plus f of x minus c t and plus 1 upon 2 c x minus c t to x plus c t g of xi dz. Now, the problem is that here your problem f of x is defined for x greater than or equal to 0. So, it means the argument of f is positive only, but and here if we take x minus c t, now if x minus c t is less than 0, then this will not be defined. So, it means that I cannot use the solution D'Alembert solution for this semi-infinite string right now. So, what we try to see here, so let us modify our problem in a bit such that I can apply this D'Alembert solution for this semi-infinite string also. So, what we try to do, we extend our this part, the other half part, in a way such that this problem, the considered problem, is a particular part of this extended problem. So, here what we do, suppose we consider an infinite string subject to the initial condition. So, let us say that consider an infinite string where initial displacement is given as y of x, initial velocity is given as v of x at t equal to 0. So, here since it is an infinite string, let us say that your y of x is given as f of x as x greater than or equal to 0. So, this is matching with your condition which is already given as for this semi-infinite string problem. So, y of x equal to f of x when x is greater than or equal to 0. Now, we are extending, we are finding this y of x as a odd extension of this function f of x. So, y of x equal to minus of f of minus x when x is less than 0. So, it means that when x is less than 0, so minus x is positive. So, minus of f of minus x is defined here. So, we can say that here y of x is an odd extension of this function f of x. Similarly, we can extend our function g of x in odd manner for the entire minus infinity to infinity, and we define v of x equal to g of x for x greater than or equal to 0 and minus of g minus of x when x is less than 0. So, now once we define your yx and vx for the entire infinite region, so it means that then I can apply D'Alembert's solution for this infinite string, and our solution is given as u equal to 1 by 2 y of x plus c t plus y of x minus c t plus 1 upon 2 c x minus c t to x plus c t v xi d xi. Now, our claim is that with the expression y and v given as follows, this will act as a solution of the semi-infinite problem also. So, we need to see whether it will satisfy all the initial and boundary condition that we have to look at here. So, here look at x equal to 0. So, at x equal to 0 your u x t will be what? U x t equal to 1 upon 2 y of c t plus y of minus c t plus 1 upon 2 c minus c t to c t v xi d xi, and w by w t you can calculate 1 by 2 c y dash c t minus y dash minus c t plus 1 by 2 v c t plus v of minus c t. Now, as we have defined the function y as odd function, it means that y of minus x is minus of y of x. So, this quantity will be 0. Similarly, v xi is also defined in a odd manner. So, it means that this integral is going to be your 0. Similarly, you can say that this y dash c t minus y dash minus c t, here I am assuming that y of minus x equal to minus of y of x. So, when you differentiate it, your what you will get, y dash of minus x minus 1 here equal to minus of y of x, y dash x. So, using this quantity is 0 and this quantity is 0. So, it means that u x t u x u 0 t is going to be 0 and w by w t at x equal to 0 x equal to 0 is going to be 0. And also that if you look at your solution which is defined as 15, it will also satisfy the initial condition, that is u of x t is equal to f of x, u of x 0 equal to f of x for x greater than or equal to 0. So, it will also satisfy the initial condition as well as the initial velocity here. So, it means that the solution given by this equation number 15 will satisfy all the initial condition and the boundary condition given at x equal to 0. And so, we can take the solution given in 15 as a solution of semi-infinite problem, and in this way our D'Alembert solution is still applicable for semi-infinite problem as well. Now, in particular, if a string is released from rest, so that initial velocity z is taken as 0, and if initial velocity g is 0, so v is also coming out to be 0, and your solution u is defined as 1 by 2 f of x plus c t plus f of x minus c t when x is greater than or equal to c t. So, argument x minus c t is positive, x plus c t is positive. So, I can define u x t as this, but when x is less than or equal to c t, then I can define as f of x plus c t minus f of x minus c t. So, here this is the small change you can say from the infinite string problem to semi-infinite string problem. Now, let us move to finite string. So, what we have done, we have considered at first the infinite string, and we obtained a solution which is known as D'Alembert solution, and then we consider a semi-infinite problem. It means that a string is fixed at one end, and then we modify our solution of infinite string to get a solution for semi-infinite string. Now, let us do the similar thing for finite string case. So, in case of finite string of length L lying along the x axis where x is between 0 to L. So, here your string is now clamped at two ends, say it is x equal to 0 and x equal to L. So, here now we want to see the vibration in this string. So, here suppose initial condition is given as u of f of x. So, it means that initial shape is something like this. So, this will represent the at this point your displacement from the initial condition is f of x. So, at any point if you look at you can find out the displacement, and let us say that initial displacement is given by u of f of x and initial velocity is given by g of x, and it is true for all x lying between 0 to L and at t equal to 0. So, initial displacement and initial velocity is given. Now, since we assume that both the end are fixed right now for this particular problem. So, it means that u 0 t is equal to 0 and w by w t at L t is equal to 0. So, it means that u of 0 t is equal to 0 and u of L t is equal to 0 here. So, it means that because here we assume that your ends point are fixed here. Now, we want to find out the solution for this finite string problem, and we try to see that the solution obtained for infinite string can be modified in a way that we can obtain a solution for this finite string as well. So, here we, as we discussed for semi infinite string, let us modify our function y of x as f of x lying between 0 to L and minus of f of minus x between minus L to 0. So, what we try to do here, we write it minus L to this L. So, here your function is something, some function is given. So, at 0 it is 0 only. So, here some function is given. Now, you define in an odd manner such that here you will get the similar thing here. So, you define y as a odd function, odd extension of f of x in minus L to 0 also. So, it means that now y x is defined between minus L to L and y of x equal to f of x in 0 to L, and y of x is equal to minus of f of minus x when lying between minus L to 0. Now, then you, since it is given only for minus L to L, then you use periodicity to extend it to entire minus infinity to infinity. So, let us assume the periodicity as y of x plus 2 r L equal to y of x, where x is lying between minus L to L and r is your integer values plus minus 1 and plus minus 2 and so on. So, y x is an odd periodic function of period 2L, and the Fourier sine expansion of such an odd function we can find out, like y of x equal to m equal to 0 to infinity f of m sin m pi x by L. Similarly, you can define your v of x as follows. Let us say g of x 0 less than x less than L and minus of g of minus x minus L x less than 0, and here also you can consider the corresponding v x plus 2 r L equal to v of x, where x is lying between minus L to L and r is plus minus 1 plus minus 2. And similarly, as y is having Fourier sine expansion, similarly you can define the Fourier sine expansion for v of x also, and we can say that v of x can be written as m equal to 1 to infinity gm sin m pi x by L, and here the Fourier coefficient, that is f of m and g of m, you can find out using orthogonality property of sine and cosine function. So, sine function here. So, here if you remember here what is the solution here, your y x is given by this. So, if I want to find out f m, then what you will do, you just multiply by sin n pi x by L. So, you have y of x sin n pi x by L d of x, and you integrate between 0 to minus L to L, right, and you and see what you will get here, it is summation m equal to 0 to infinity f of m sin m pi x by L into 0 to L, and then here you will get within product sin of n pi x by L d of x, and then use orthogonality property of sin n pi x by L, and you will see that your f of m you can obtain by this, it is 2 by L 0 to L f of xi sin m pi xi by L d xi. Similarly, you can obtain gm, that is 2 by L 0 to L g xi sin m pi xi by L, and if you look at both y and v are similar to each other, in fact it is kind of symmetric. So, once we have the expression for y and v, we can write we can substitute in our relation. So, here our solution 1 by 2 y of x plus ct plus y of x minus ct, you can write it m equal to 0 to infinity m of f of m sin m pi x by L into cos of m pi ct by L here. So, here using this, similarly you can obtain 1 upon 2 c x minus ct x plus ct v xi d xi equal to L by pi c m equal to 0 to infinity gm by m sin m pi x by L sin m pi ct by L. So, here we simply use expression y of x as this, and you when you have this, then you can write f of y of x plus ct as 0 to infinity m equal to 0 to infinity f of m sin of m pi x minus x plus ct by L. Similarly, you can write y of x minus ct and then you simplify. Then you can use sin of a plus b plus sign of A minus B formula, and you can get the formula series exponential like this. So we have this part, we have this part, so we can write down our solution uxt as m equal to 1 to infinity fm sin m pi x by l cos of m pi ct by l. This is corresponding to 1 by 2 y of x plus ct plus y of x minus ct, and then corresponding to integral part 1 upon 2 c x minus ct x plus ct v xi d xi, we can write down this expression and we have this. So we can write uxt as m equal to 1 to infinity fm sin m pi x by l cos m pi ct by l plus l by pi c m equal to 1 to infinity gm by m sin n pi x by l sin m pi ct by l, and here the coefficient fm and gm you can obtain using the expression here 18 and this 20. So it means that your solution is given as this. So now we have obtained this solution using D'Alembert's solution for infinite string, and we modify our problem in a way such that we can utilize this D'Alembert solution for finite string as well. Now let us look at the same problem, and now you try to find out the solution using variable and separable method. So here we consider a thin homogeneous string which is perfectly flexible under uniform tension, lie in the equilibrium position along the x axis. The ends of a string are fixed at x equal to 0 and x equal to n l, that we lying it x equal to 0 here and x equal to l here. The string is pulled aside a short distance. So once we have this thing, then you simply pull along one side, then it is something like this kind of figure, and released. And if no external forces are present, which correspond to the case of free vibration, so it means that here once we put it like this and then we simply leave, right. So it means that no other force we are applying after that. So it means that at initial position it is simply left. Then we try to find out the vibration of this string, and the subsequent motion of the string is described by the solution uxt of the following problem. The following problem is this: it is PD utt minus c square uxx equal to 0, x is lying between 0 to L, t is greater than 0, and boundary conditions are what? If you look at, we have taken the end fixed, so x equal to 0, u0 t is 0 and ult is also 0, because at the other end also it is fixed. So u0 to 0 t is 0, ult is equal to 0, and initial condition is given as ux0 equal to f of x and utx0 is some g of x. So here we consider the same problem, but now we try to solve in a different manner using separation and variable method. So to obtain the variable separable solution, we assume that uxt is equal to xx t of t. Now here please remember here that you cannot apply your variable separable method for any problem. Here you need to have your problem separable as well as the boundary separable. So it means that you have to choose your coordinate system in a way such that your equation is separable as well as the boundary is also separable. We will see that here both equation as well as the boundary condition are separable to each other. So let us see what I mean. So here if you put uxt equal to xx tt, then your solution is what? It is your problem is what? utt equal to c square uxx. Then you will write t double dash x equal to c square x double dash t, divide by xt. So you will get t double dash upon c square t equal to x double dash upon x. That is what it is written here. So x d2 t by dt square equal to c square t d2 x by dx square, and then you divide by c square xt, and we have this equation that d2 t by dt square divided by c square t equal to d2x by dx square divided by x equal to k here. Now here this k is a separation constant. So it means that we can write our equation like this: d2x by dx square minus lambda square x equal to 0, and d2t upon dt square minus c square lambda square t equal to 0. Now here let us consider three cases for these constant k here. So k, let us assume that k is positive, negative and 0, and we try to find out the non-trivial solution in each cases. So here basically it is a eigenvalue problem, stem level problem, and we have already discussed the similar stem level problem when we discuss the boundary value problem. So now we can find out the solution of these problems as x of x equal to c1 e to power lambda x plus c2 e to power minus lambda x, and similarly you can write down tt as c3 e to power c lambda t plus c4 e to power c lambda t. So now our solution uxt is written as c1 e to power lambda x plus c2 e to power minus lambda x into c3 e to power c lambda t plus c4 e to power minus c lambda t here. Now we have to obtain 4 constants c1, c2, c3, c4. So here we will use the boundary condition. So boundary condition are what? It is u0 t equal to 0 and ult equal to 0. So when you put your solution, this is x of 0 t of t equal to 0, and similarly x of l t of t equal to 0 here. So here since t of t cannot be ideally equal to 0, so this implies that x of 0 is equal to 0 and x of l equal to 0. So using this you can solve this problem. Your x of x is what? X of x is equal to c1 e to power lambda x plus c2 e to power minus lambda x. So it is c1 e to power lambda x plus c2 e to power minus lambda of x. So use x is 0 equal to 0. So what you will get? It is 0 equal to c1 plus c2, and xl 0, it means this is 0 equal to c1 e to power lambda l plus c2 e to power minus lambda l. Then you want to find out c1 c2. So c1 c2 you can find out using this matrix equation. This is 0 0 and you can get here 1 1 and e to power lambda l e to power minus lambda l, and if you see that this determinant is non-zero, so we can say that here I will get only a trivial solution, that is c1 equal to c2 equal to 0. So it means that in this case we will have only a trivial solution. So if since this value is non-zero, implies that lambda has to be 0. So this value determinant has to be have value 0 provided your lambda is equal to 0, but lambda we have assumed that lambda is non-zero, because here we have assumed that k is greater than 0 here. So it means that lambda cannot be 0, but this determinant is having 0 value when lambda is equal to 0. So it means that it is against our assumption in this case. So hence our solution is non acceptable, means your in this case when k is positive, we will not get any non trivial solution. So here what we have seen here, that in case when k is positive, we do not have any trivial we do not have any non trivial solution. So now let us consider next case, that is let k is equal to 0 here, and in this case our equation is reduced to d2x by dx square equal to 0 and d2t by dt square equal to 0, and in this case you can find out your solution as x of x equal to ax plus b and tt equal to ct plus d. Again, as we have pointed out, the solution uxt is written as ax plus b into ct plus d here. Now our initial condition is what? Initial condition we have seen that it is say x of 0 equal to x of l here. So our solution is x of x equal to say ax plus b here. So put x 0 equal to 0, so this implies that b equal to 0, and then when you put xl equal to 0, then it is al equal to 0, and since l is non-zero, so this implies that a is equal to 0. So here this x of x is coming out to be ideally equal to 0. So in this case using the boundary condition, we have u0 t equal to 0 into b ct plus d implies that b equal to 0, and similarly we can say that a equal to 0. So here also this part is completely 0, so it means that uxt is only a 0 solution. So it means that when k equal to 0 also, then we do not have any non trivial solution. So this case is also we will leave. Now, let us consider the third case, that is k is less than 0. So, in this case let us assume that k is equal to minus lambda square, and the corresponding differential equation is d2x by dx square plus lambda square x equal to 0 and d2t by dt square plus c square lambda square t equal to 0. So, here general solution is given as corresponding to this general solution is c1 cos lambda x plus c2 sin lambda x, and corresponding to this we have c3 cos c lambda t plus c4 sin c lambda t is given. Now, you try to fix your c1 and c2, and you can see that how we can fix this c1 and c2. So, here let us say we have problem c1 cos of lambda x plus c2 sin of lambda x, and that is your x of x. So, we let us put x of 0 equal to 0, and that implies that your c1 has to be 0, then x of l equal to 0 implies that c2 sin of lambda l equal to 0, and if we take this c2 is 0, then we will again get a trivial solution. So, we want that this lambda l to be chosen like here n pi. So, let us say lambda is equal to n pi by l, where n is taken as plus minus 1 plus minus 2 and so on. So, it means that if we take lambda as n pi by l, then we will get a non-trivial solution. So, it means that let us see, this implies that here you will get a non-trivial solution provided this lambda is n pi by l, which is given here, that using the boundary condition u0 t equal to 0 we get c1 equal to 0 as we have pointed out, and using the boundary condition ult equal to 0 we have sin lambda l equal to 0. This implies that lambda is written as n pi by l, where n is 1, 2, 3 and an integer value, which are the eigenvalues corresponding to the eigenfunction sin lambda. So, here you can write down this solution as u n x t equal to sin n pi x by l, a n cos n pi c t by l plus b n sin n pi c t by l. Here I am just using the value lambda as n pi by l. In this case, here you use c1 is 0, so this is gone, and here sin n pi by l x is there. So, you just replace the value of lambda, and since this is true for every n, so we can write down for every n, we can write down the solution u n x t as sin n pi x by l, a n cos n pi c t p by l plus b n sin n pi c t by l. Now, since for each n we have a solution then of the homogeneous problem, then if you take the this summation from n equal to 1 to infinity, then also it will remain the solution of this homogeneous problem. So, using the this is known as a superposition principle, that if we have a homogeneous problem and we have V1 and V2 are two solution, then linear combination of V1 V2 will also be a solution of the homogeneous problem, and this is known as superposition principle. So, using superposition principle we can write down our solution as uxt equal to n from n equal to 1 to infinity sin n pi x by l, a n cos of n pi c t by l plus b n sin n pi c t by l. Now, here your coefficient a n and b n is still unknown. So, to find out the coefficient a n and b n we will use our initial condition, that is ux0 equal to f of x. When you put t equal to 0, then this part is gone. So, you will get a n and cos of n pi c t by l is going to be 1. So, you will get ux0 equal to a n sin n pi x by l. So, that is what we have written, ux0 equal to n equal to 1 to infinity a n sin n pi x by l, and we already know the value of ux0, that is given as f of x. So, now with the help of this we try to find out the value of a n. So, how to find out value of a n? So, here you just multiply the by sin m pi x by l. So, let us consider this problem. So, here we have your f of x equal to summation a n sin n pi x by l. So, multiply both side by say sin m pi x by l into f of x dx and integrate between 0 to l here, which is given as summation integrate between 0 to l a n sin n pi x by l into sin m pi x by l and dx, and we say that this I can write it summation a n assuming that this infinite series is uniformly convergent. So, we can write it here n equal to 1 to infinity a n 0 to L sin n pi x by L sin m pi x by L d of x here. So, using the orthogonality, we say that if m is not equal to n, then this value is equal to 0, and when m is equal to n, or you can say the value a n, this n is equal to m, then this value is coming out to be L by 2. So, we can write the value a m L by 2 is equal to 0 to L f of x sin of m pi x by L d of x. So, in this case we can find out the coefficient a m as 2 by L 0 to L f x sin m pi x by L. So, that is what we have written here, a n equal to 2 by L 0 to L f x sin n pi x by L dx. Similarly, using the next condition, that is ut x 0 equal to g of x, and that you can get it from n equal to infinity b n sin n pi x by L into n pi c by L. So, that we have obtained here from this equation. You differentiate with respect to t and put t equal to 0, you will get this relation that ut x 0 equal to n equal to 1 to infinity b n sin n pi x by L into n pi c by L. Now, this value is given as g of x. Again, using the orthogonality property, we can write b n as 2 by n pi c 0 to L g x sin n pi x by L dx. So, here we require the solution as obtained by, say, this equation number 32, that is u x t equal to n equal to 1 to infinity sin n pi x by L a n cos n pi c t by L plus b n sin n pi c t by L, and the coefficient a n and b n is obtained in equation number 33 and equation number 34. So, it means that once we have a n b n given to us, then we can write down the solution for this finite string problem as equation number 32, I think 32, and here the u n x t given by equation 31 are called normal modes of vibration, and the corresponding frequency omega n is equal to n pi L by c are called normal frequency. Then next result is uniqueness of the solution for the wave equation. So, as we have discussed the variable separable method to find the solution to the wave equation with certain initial and boundary condition for, say, finite boundary value problem. So, it means that in a finite string which is say fixed at the end x equal to 0 and x equal to n, we have found out the solution using variable separable method. But if you remember, we have also discussed the same problem and we found the solution using D'Alembert's solution of string, and we came to know that both are coming as same. So, now how it is coming here. So, here in this particular part we prove that the solution of one dimension wave equation with finite domain is a unique solution. So, it means that whether I will use D'Alembert solution or say variable separable method, our solution is coming out to be unique. So, it is up to you whether you will choose D'Alembert solution or say this variable separable method, the solution is coming out to be same here. So, let us do this problem. So, this is the uniqueness theorem. The solution to the wave equation u t t equal to c square u x x plus f of x t. Here x is lying between 0 to L, t is greater than 0, satisfying the initial condition, that is u x 0 equal to f of x, x is lying between 0 to L, u t x 0 equal to g of x 0, x lying between 0 to L, and boundary condition u 0 to equal to f 1 t, u L t equal to f 2 t, where u x t is a twice continuously differentiable function with respect to x and t is unique. Now, here you note down certain things, that here we are writing this function f of x t. It means that we are also considering the external force. It means that it is not say the string is not left say at initial position f of x and g having initial displacement f of x and initial velocity as g of x, but for every x and t we are also applying an external force which is given as f of x t. And also that here your endpoints are not fixed. In fact, endpoints are given as f1t and f2t. It means that the endpoints are not fixed. In fact, that is also depending on the some function, say f1t and f2t. So, at t is increasing, your initial displacement is also the endpoint is also moving kind of thing. So, it is a moving endpoint problem, and we say that if it is a if it has a solution, that solution must be unique. Now, the case which we have discussed earlier is a special case of this, by assuming that f of x t is 0 and f1t and f2t are 0. So, it means that it is a special case of this uniqueness theorem. So, it means if this problem has a unique solution, the special case will also have a unique solution. So, now let us try to prove this result. So, here suppose u1 and u2 are two solutions of the given wave equation 35 and satisfying these initial and boundary condition. Then suppose that we have two solutions, and now we want to show that these two solutions are identically same. So, let us assume that v is equal to u1 minus u2. Then this function v is a solution of the following problem: vtt equal to c square vxx, x is lying between 0 to l, t is greater than 0, vx0 is equal to 0, vtx0 equal to 0, and v0t and vlt is coming out to be 0. So, it means that if you look at here, our problem is what? Our problem is utt equal to c square uxx plus f of xt, and u0t is equal to f of x, u f of x, and ut u of x0 is equal to ut of x0 equal to g of x, u of 0t equal to f1t, and u of lt equal to f2t. So, now you let us say u1 and u2 are two solutions. So, it means that u1 will satisfy the same equation and u2 will also satisfy the same equation. Then when you look at the u1 minus u2, then this part will be cancelled out, this part will also cancel out, because it is independent of your u1 and u2. So, it means that now you can write it here that the corresponding solution satisfied by u1 minus u2 will have will not have this part, this part, this part, and this part. So, it means that the corresponding difference u1 minus u2 will satisfy the homogeneous problem like vtt equal to c square vxx and the homogeneous initial and boundary condition. Now, we want to show that here your vxt is identically equal to 0, and to prove that, here we consider the function et equal to 1 by 2 0 to l c square vx square plus vt square dx. Now, we want to show that how we show that vxt is 0, by showing that its partial derivative are 0. And how we can show that partial derivative are 0? Here we show that this function et is coming be 0. So, it means that if this function, which is known as generalized energy function, if generalized energy function is 0, it means that your string is lying in a equilibrium position. That is the idea which we have started, that if we do not have energy, then we will like to be in equilibrium position. So, here let us say that et is equal to 1 by 2 0 to l c square vx square plus vt square dx, and which represent the total energy of the vibrating string at time t. Now, differentiate with both side of 37 with respect to t. So, d by dt equal to 0 to l. Now, here when you differentiate c square vx square, so it is 2 vx vxt, and here it is 2 vt vtt. So, we will write it here 0 to l c square vx vxt plus vt vtt dx. Now, integrating by part this part with respect to integrate this part with respect to say dx. So, when we have 0 to l c square vx vxt dx, this we write first integration of second. So, we will get c square vx vt between 0 to l minus 0 to l c square vt and vxx. So, here integrating this thing and differentiating this. So, we will get 0 to l c square vt vxx dx. Now, if you look at this boundary term c square vx vt lying between 0 to l, our claim is that it is 0. How we can show? Since v0t is 0, so it means that if v0t is 0, then vt0t is also 0. Why? So, here if you look at v0t is 0 means what? v0t is equal to 0 for all t. So, it means that if you want to calculate vt0t, then it is what? Limit say s tending to 0 v of 0 t plus h minus V of 0 t divided by h. Now, since it is true for all t, so this implies that limit s tending to 0, this value is also 0, this is already 0. So, it is nothing but 0. So, V t 0 t is coming out to be 0. So, here V t 0 t is 0, and since V L t is equal to 0, so in a same manner we can say V T L t is also 0. So, it means that this boundary term is gone, is it okay. So, it means that our equation number 38 is reduced to d by dt equal to 0 to L. In place of 1 we are writing here minus 0 to L c square V t V x x. So, if we take out this V t term out, because here we have V t V x x and here it is V t V t t. So, we can write V t times V t t minus c square V x x. Now, if you look at V is a solution of homogeneous problem, it means that V t t minus c square V x x has to be 0. So, it means that since V is a solution of homogeneous problem, this d by dt is coming out to be 0. So, it means that E is constant with respect to time t. So, here E t is constant, let us say constant value is c. Now, if E t is constant and we already know that if V x 0 is 0, so V x x 0 is 0. In a similar manner we can prove that if V x 0 is 0 for all x, then the derivative of V x 0 with respect to x is again 0. So, this also we can see like this, if V x 0 is 0, simply we want to find out V x of x 0, that is limit say s tending to 0 V of x plus h comma 0 minus V of x comma 0 divided by h. Now, this is 0, this is 0, so it is coming out to be 0. So, it means that V x x comma 0 is 0, V t x comma 0 is 0. So, we can calculate E of 0, E of 0 will be what? E of 0 is equal to what? 0 to L c square V x 0 0 t and V t square 0 t. So, when you do this, your this value is coming out to be 0, this value is coming out to be 0, and hence E of 0 is coming out to be 0, but since E t is constant, so it means that this constant value is coming out to be 0. So, it means that E t is 0 for all t. It means that this is possible only when the integrand is what? Integrand is c square V x and V t square, these are 0, because integrand is non-negative value. So, it means that V x is 0 and V t is 0. So, it means that V t is 0 and V x is 0 for all t greater than 0, and if partial derivative are 0, so it means that we say that it is possible only when V x t is constant with respect to x as well as with respect to t. So, it means that V x t is constant, but we already know that V x 0 is 0. So, it means that this constant value has to be 0. So, it means that V x t is 0 for all x and for all t. So, it means that if V x t is ideally equal to 0 means V x t is what? A difference of two solution. It means that difference of two solution is ideally equal to 0. So, it means that u 1 x t is equal to u 2 x t. So, this shows that the solution of the wave equation for finite domain is unique. So, whether you apply the separable variable method or say D'Alembert's wave solution method, both are coming out to be same. So, with this I will end our lecture, and we will continue our lecture and next lecture. So, thank you for listening us. Thank you very much.